Okay, hey everybody, welcome to UW-Stout. UW-Stout. It's good to see so many happy people from the town of Colfax, or near Colfax, if not in Colfax. My name is Martin Andres, Dr. Andres. This is Dr. Matthew Gray. And I no longer teach here, so I've taught at Stout a long time. Maybe longer than your parents have been alive, over 38 years. And I retired about a year and a half ago. But you know what? For all the years that I was here, I loved chemistry. I loved teaching chemistry. And I'm especially happy to have a chance to be back here one more time. This might be my last time doing this. As a kid, I had 2 or 3 chemistry sets, and I loved those. I loved playing with chemistry, and this is about as close as I can come to chemistry. So anyway, welcome. I know your teachers, Mrs. Succo and Mrs. Dilladil, very well because my wife, Mrs. Andres, taught 6th grade at Colfax students here. So anyway, welcome. And I'm going to let Dr. Ray tell you a little bit about himself. He's the person who came to Stout when I left.
Yes, I have some big shoes to fill here, so I'm taking over where Marty left off. And so I teach several courses here, like general chemistry, as well as chemistry of plastics, chemistry of polymers, as well as chemistry of materials. Those are the areas that I focus on here. And so we are obviously very happy that you're all here today. We hope you enjoy the presentation we're going to give. So go ahead and get started.
Okay. I'm going to try to sort of walk you through the things that we're doing. And so what we want to point out to you is that this is science. Chemistry is a science. And when we do science, our goal is to explain what we see. Sometimes things look pretty magical, and there's always an explanation. So I'm going to start out with one of my favorite magic tricks. I'll bring this up to the front, hopefully everybody will be able to see it. When I was teaching here at Stout, I always walked around with my coffee cup. I love to drink coffee. And this Hewlett Packard cup was my favorite coffee cup. And there's a good reason why. I'll try to do this so that everybody can see this really well. Put the cup right here. I think that'll work out well. That cup is bigger than you think. Looks like an ordinary cup. Now this is my Gilman Sciences cup. Not nearly as good. You take my popcorn and put it in that cup. It's amazing how much popcorn that cup will hold. And just help it get down in there. And with a little bit of time and effort, I can put all this popcorn into that little cup. And I've had students say, well, there must be a hole in the bottom of the cup. There isn't. No hole in the bottom of this cup. In fact, we'll hold it up here so that you can see that nothing's coming out of the bottom. And we'll just keep on adding our popcorn. And you know, I'll tell you what. I'll ask a question in a minute. I'll let you guys keep your hands down. And then I see some hands over here, and I'll ask a question. There's something in this cup. Okay. What do you think? Say it again. Very good. You know, that's such a good answer. I'm not even going to go any farther with the answers. Lots of times people will say, oh, there must be acid in the cup. And I'll always say, well, if there's acid in there, I wouldn't want to put my finger down it. But I can, and it doesn't hurt. But there is something in that cup. Yes, sir.
Is it water?
It isn't water. That's also a good question. Let me just set this here for a minute. Dr. Ray, would you just show them? Here's some styrofoam. Would you just maybe put it on some water? You probably use that. If that's water in that, you just float a little on the water and show them that styrofoam water. So it's not water. It's actually a chemical that you can buy. You buy it at the in the paint department, and it's called acetone. So the popcorn that we're using, of course, is a plastic polystyrene, and we have that up on the slide also, polystyrene. But the liquid that we have in there is acetone, and Dr. Ray was just holding up the acetone. So I think that's about as much as I'm going to put in there. But we could spend the next hour putting it in there. Here's the interesting thing.
Got a little bit of acetone here. We can see what happens
Okay.
without any disappears.
Can you try something? As long as you're doing that. One of my McDonald's cups. Let's, would you just pour your acetone into that cup? If you come around to the front and we'll do this so that everybody can see, I'll hold the cup over that. While we're doing this, we might as well have a little fun with it. bottom came out of the cup.
So you don't want to drink this stuff for a lot of reasons.
Right. If we take, let's see, what did I, there it is. If we take this, and now I will pour the acetone that was in here out. And you know what? I may have a little too much. I don't want to have it flow. I'm going to pour the rest in. And now we'll take that styrofoam and pour it out. Oh, that's not styrofoam. Where is it? Here it comes. There it is. That little bit of plastic that's coming out is the styrofoam that you saw. And in fact, there's a little more of it. It's not too bad. You can actually, it's sort of like putty. I'll pass it around. Don't eat it. and after it dries, it gets brittle like this. This is actually plastic. This is the same plastic that model cars and model airplanes are made out of. And when you use the glue to glue the pieces together, it actually dissolves the plastic and causes it to piece together. So that's our first magic trick, and we've given you the explanation for it. Oh yeah, are they getting pretty messed up? I think it'll be good after that. Yeah, just get the rest of it after a while. Yes. It is. Hey, did everybody hear that question? That was an excellent question. The chemical that we just used is in nail polish. Okay, the next thing we're going to do, and Dr. Ray, stay up in front here. We need a volunteer. Okay, I saw that in the second row, the young lady with the gray sweater on. Come out front, stand right next to Dr. Ray. I just want to show you. I'm going to get behind the counter for a minute. I've got another one of my McDonald's cups here. I'll put some water in it. And I will take my pencil, push the pencil down through the cup. And you can see that the water comes right out. No problem. And I'm going to keep it from coming out. And I'm going to just grab myself another cup. And I'm going to pour this water into this cup. And actually, you know what? I want a little bit more. I want to make sure I have enough. Pour a little more in there. And now, what's your name? Mackenzie. We love volunteers. Dr. Ray, will you hold this over here? Of course. And I will put it out there.
Uh-oh, what's up?
Wow. Well, no, we didn't. That water is still in there. We could. Yeah, we could have more. Oh, yeah. And it still doesn't come out. And in fact, let's see. small amount of a plastic called sodium polyacrylate in that cup. And when the water hits the sodium polyacrylate, absorbs by sodium polyacrylate, it forms a gel. And you could even test this now.
Oh, you could. It would be a little bit messy, but just make sure you don't. I wouldn't hold it in your hand when you can touch it.
Yeah, you can just put your finger in it. They're like
Anybody have any idea what that material might be used for? Diapers. Exactly correct. That is in every baby diaper is where it is. There's no match. All right.
Okay. Something very closely related to that. Yesterday, I found some crystals. I don't know if these are really crystals, little chunks of a plastic called polyacrylamide. And you can see that they're not very large. I've got a few in the speaker. Polyacrylamide is that chemical right there. You can see that actually plastics are very long molecules. And what we've drawn on the board is just a short segment of a long plastic molecule chain. Plastic molecules are like long chains. Polyacrylamide is similar to sodium polyacrylate. But the difference is this doesn't absorb water quite as quickly. However, what I did yesterday when Dr. Ray and I were getting ready, I added some water to this beaker. It had the same amount of polyacrylamide in it. And now what we're going to do is pour the water out. Oh no, look at that. I'll just reach in and grab one of those crystals. Okay, let's get a big one. Get a few. This is what happens to them after they're in the water overnight. In fact, let's pour the water out. And actually, if they sit in there for a longer period of time, they'll even go larger. They absorb hundreds of times their own weight in water. So this is polyacrylamide. Does anybody now question? Okay. Does anybody know where this might be used? Yes.
Little balls in the plant that you put in water overnight and they'll argue and then you put the water in there.
That's exactly right. In fact, I think they're even using potting soil. If you go to Kmart or Walmart or someplace and buy some potting soil for your house plants, sodium or polyacrylamide gel.
Store in the water for use later. Much faster than it would be able to make more than it would do otherwise. Evaporation makes the plant stay wet longer.
Oh, that's right. We're showing you a bunch of things that are kind of magic tricks, and they're pretty magical. We've got another one here. Oh, I love this one. Yesterday, we had to heat this to get it to look like this. This was a solid for yesterday. It's mostly solid. There's actually some water in here, but there's a chemical called sodium acetate. And tell you what, it'd be nice to have another volunteer. Okay, I'll take the young man on the end right over here. Third row, come on down. You would just hold this for everybody to see. That's what we call a supersaturated solution. What we did is we heated it up to get the sodium acetate to dissolve, and then we let it cool very slowly. And instead of the sodium acetate coming back out of solution like it should have, it stayed in solution. But if we add one little crystal of solid sodium acetate, this is solid sodium acetate in this bottle. We've got one little crystal on the tip of, I don't know if you can all see that. We're going to take that black stopper out and hold that bottle up real high so everyone can see it. We're going to add one crystal of sodium acetate. Everybody watch this now. As you crystallizing. What we did is we added a seed crystal. When they try to get, when we have a drought and they seed the clouds to try to get it to rain, they actually add crystals of silver iodide, because silver iodide crystal structure is in the ice, and it helps form ice crystals in the clouds. So now we have our solid sodium acetate, and we have a little bit of water. Not very much water in there, but a little bit of liquid water. So all of that sodium acetate is dissolved in a little bit of water. And what we're going to do, we'll do that one more time. If we'll give you to hold this one, stand right here. We'll do that same thing again over on this side. We'll add one crystal of sodium acetate. Well, this time you got two crystals. You hold it up really high, and everybody can watch it crystallize. It's interesting, too, that we had to use heat to get it to go into solution, to get it to dissolve. Now, as it's crystallizing, it's giving off heat. You feel the bottom of this. It's getting a little bit warm. It actually gets warm. They actually make hand warmers. Sometimes hunters use them, and they use them, they put them in their pockets, they make it crystallize like that, and then they keep their hands warm when they're out hunting, fall or in winter. So that's our super saturated solution. Question up front. That is such a good question. The answer is yes. And in fact, this one has probably been used about 100 times. And you can take it, put it in a microwave, heat it for about a minute, it dissolves. Then you have to let it cool. And when it cools back down to room temperature, you can get it. One more question and then we'll move on. Many heat packs use that reaction. There are other reactions that are sometimes used also, but the ones that are reusable use this concept. Okay.
So the quick background on pH, you can see the Coke product up there. Diet Coke is great to drink. You see it's very acidic. So we deal with acids and bases all the time. We've got club soda, we've got vinegar, we've got things like Drano, different soaps. So pHs, acids, and bases have a big range of acidity or basicity you can have. And so that is quantified using a scale called the pH scale, where low numbers are acidic, they're acid, like vinegar, or like orange oil, and very basic things like sodium hydroxide or phenol ammonia, you might have seen others use, are toward the high end. And things like water or our body's fluids like blood, those are usually going to be right in the middle, neither very acidic or basic, almost neutral. So, Dr. Runners is going to show us some interesting color changes.
Are we going to use the pH probe on these? Okay, all right. This is the first time Dr. Ray and I worked together in this, so there's some things we're not quite sure of, but I think we can show you a couple of things very quickly. We have a whole bunch of different, well, first of all, we have an acid and a base. And this is sodium hydroxide, and this is hydrochloric acid. Sodium hydroxide is the base, hydrochloric acid is the acid, and you can see on the screen that hydrochloric acid is HCl, reacts with sodium hydroxide, NaOH, to form water plus salt. And they react together to salt. The same salt that you form your food. So even though either one of those, if you drink either one, it probably make us really sick. When we react together, it forms something. So we have various indicators, and what should we start with? Let's start with let's try the green one. Brome sea salt green. We're going to add a bunch of drops of brome cresol green. I always wonder why it's called brome cresol green when it looks like blue. Maybe we'll figure it out. It does. And cool, isn't it? Dr. Ray is going to, we'll let that mix well. He's going to add, what do you want to add? Start with that hydrochloric acid.
All right. We've got hydrochloric acid. We're going to add this dropwise and see what happens to that color. So that's telling us now that that is now acidic because we added acid to neutral water, and so we saw a color change that went from blue to yellow. Well, just like many chemical reactions, this is a reversible reaction. So if we were to add the base again, what do you think will happen? It'll turn blue? Well, let's see what happens.
Blue and yellow make green.
It's still blue. I like that blue.
So I suppose when it's in between, that's green. Maybe that's why they call it brome cresol green.
That tells you when it's neutralized. So when the yellow and blue present, it will look green. That tells you you're right at that neutral point in between the two. So the green color occurs right when you know it's neutral, which is very useful for chemistry problems where you're trying to make a neutral pH.
We've got a number of different names of indicators up on the slide. The second one down is phenolphthalein. I actually, on my shirt, this is a UW-Stout chemistry shirt, says we can spell phenolphthalein. And that's a hard one to spell. But we have some phenolphthalein somewhere here. Here it is. And we'll add some phenolphthalein to this glass. Dr. Ray, would you do the honors?
Yes. So what do you think is going to happen with this glass?
Red.
Think it'll turn red?
It's going to do that big
The big steam thing?
Yeah.
You have some differing opinions. So let's see what happens when I add some base here.
Oh, yeah. It's purple. It's purple.
We got pink and blue up here now.
You know, not too many years ago, phenolphthalein was the active ingredient in a commonly used product.
Shampoo.
Called X-Lax.
What's that? It's a laxative. And now it's no longer, it's now illegal. I think they found that it might cause.
But you would not want to drink the pink liquid. I'll just tell you that. It wouldn't kill you, but it would make you feel uncomfortable for a while.
Just to show you, if we add hydrochloric acid to it,
It's reversible. As what it is.
now we'll try to go the other way. It takes a while. So that's now the phenolphthalein is telling us that this is acidic. The brome cresol green is telling us that that's basic. We add hydrochloric acid to that. I like the other colors better, but that's all right. Oops. And then we do a little more hydrochloric acid.
Yeah, it's part of it.
That's all right. That's good. So we could do some more acid-base indicators, and in fact, we probably will show you one or two other things related to acid-base indicators. Let's get that together. What's next on our agenda?
All right, next up is a clot reaction. So, Dr. Under's favorite. Oh yeah, this will be very exciting.
Yeah, this is an interesting reaction. You know, chemical reactions are interesting because some of them are extremely rapid. We're going to show you later on in the explosions. Explosions are very, very rapid chemical reactions. There are other chemical reactions right now in your body. We've all got chemical reactions going on. My car is sitting out in the parking lot, and you know what? It's rusting. Not very fast. Might take 10 years before I can tell that it's rusting. But there's the rusting process of a very slow chemical reaction. This particular reaction, Dr. Ray, would you come up on here and hold this for me, and I'll pour some things into it. This is a reaction that is sort of in between it, not real fast, not really slow. And I made this one up yesterday. I made it up to take about 40 seconds. So if you have a watch on and can time this, we'll see how close to 40 seconds this is going to be. I have about 5, 10. Am I a little slow here? 15.
Suspense is killing me.
Yeah, it's going to go up. 25.
Quick.
30.
An exercise in patience.
Oh, it's wonderful.
I had 45.
Did you have about 40? Okay. So we were pretty close. Now, what we need are 5 volunteers. Dr. Ray, will you put a couple over there and I'll put a couple over here? And oh, yeah. Oh, no, you'll have to stay. We'll get you for another. Do we have 5 now?
Oh, I guess we got 5.
We're good. We're good.
I think you're next. Sorry about that.
Yeah, we'll have everything. All right. Dr. Ray, will you help me give these to, distribute those to the first person. I'm going to tell everybody what they're going to be doing. We're going to start on this end with you. Cameron is going to be the starter here. What he's going to do is fairly quickly, I want you to pour the small one into the big one. And then I want you to hold that big one up so everyone can see it. And if you want to turn around and set the small one on the table after you pour it, you can do that. But you got to hold the big one so everybody can see. I'm going to count to 5, and then you're going to pour it. I'm going to count to 5, and you're going to pour it. I'm going to count to 5, and you will. And finally, I'll ask you. Okay, are you ready? 4. Perfect. 1, 2, 3, 4, 5. Perfect. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, Camden's the man over here, and we're going to watch his beaker. We'll see if this really is a clot. If this is a clot reaction, it should be pretty predictable. We'll see if it is.
Oh, yeah.
Oh, there we go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Nice job, you guys. All right.
42 seconds.
You don't want to do that. use potassium iodate and sodium bisulfite, and it forms a chemical called iodine, which reacts with starch. And it's a very complicated reaction. Dr. Ray.
All right, so this next one is a favorite of mine from way back. My mother used to let me take vinegar and soda and a big cookie sheet and just make as much of this foam as I wanted. But I'm going to do this in a way that allows us to capture the gas that is given off. And so I've got a bottle of water here with 2 hoses that come out of it. I am going to need a volunteer, and since I already showed you last time, we'll give you the chance now. All right, so here's what we're going to do. So your job is going to be pay attention to this hose and make sure when the liquid starts coming out, it's going into this basin. Okay? So right now, I just want you to hold it nice and tall so nothing leaks out. All right, so I'm going to invert this bottle here. So if you could also hold that one up for a moment. Thank you. So I've already put some vinegar in this bottle. This is just regular household vinegar bought in the grocery store. And in this little container here, I've got a piece of tissue paper that has some baking soda in it. And this is just regular baking soda, like what you would also get at just the grocery store. So I just got baking soda that's in a tissue. So we're going to carefully put this in here, hopefully not breaking it, which would be fun for us all. Okay, so we're carefully doing this. So now, I'm going to put the cap on. So go ahead and point that down now. So this is a little bit slower than some of the reactions you might have seen, but we're going to collect some gas. So I'm generating the gas in this bottle. It's flowing through this pipe and collecting into this pot bottle. And it's displacing the water which is coming out of this hose just like a fire hose here.
Oh, cool.
So I'm capturing all that gas. And you see up on the board what we're doing is acetic acid plus sodium bicarbonate, which is going to sodium acetate plus water plus carbon dioxide. And just so you realize, sodium acetate that we're forming is the exact same chemical structure as the sodium acetate that we looked at earlier. So that's a byproduct of this reaction. So now we've created our carbon dioxide, our water, and our sodium acetate. Now this bottle is completely filled with carbon dioxide gas. Thank you very much for your help. I appreciate that. All right, so how can we prove to ourselves that this bottle that has seemingly nothing in it contains carbon dioxide gas? So I'll cap that here quick. This bottle's now full of carbon dioxide. How are we going to do this? Well, there's a couple different ways we can prove this to ourselves. The first is what's called an instrumental method. I have a electrical instrument up here that allows me to see carbon dioxide gas. So, make sure this is functioning at the moment. Looks like it is. And so this is an instrument called an infrared spectrophotometer. Okay, it's a mouthful. So what this does is it looks at certain wavelengths of light that things can absorb, like carbon dioxide gas. So what we're going to do to begin with, we're going to start collecting data. You'll see this little plot at the bottom here. We'll start marching across, hopefully, if I've done it right. So we're going to collect some data here. So it's going to be in light blue. You should see that little blue line going across the bottom. So if I take this and I carefully pour some of this into the instrument up here, we should notice the change. Notice that the numbers, unfortunately, it's in light blue. But we can see that it's climbing. So this is tuned to carbon dioxide, and you see that it has climbed up. Now it's 0.4 as a reading. So let's try to begin with. When I poured it in, we're proving that this was carbon dioxide. We can blow it away, and we can make it go back down to normal. But that's not the only way that we would be able to determine if this is carbon dioxide gas. there's another way. So let's take a look at that way as well. So, who knows what is necessary for something to burn? Anybody? Yes. Oxygen. Oxygen is necessary for things to burn. Excellent point. So what I'm going to do is I'm going to light these two candles in this little fishbowl here. We're going to allow these to burn. So I am going to need one of these hoses, and then the others to go out of the way. So what I'm going to do now is I'm going to feed that carbon dioxide gas into that fishbowl so that we can see what happens if we remove one of the reactants from this equation above. You see paraffin wax, which is what that candle is made out of, plus oxygen, 38 oxygen molecules for one paraffin wax molecule, is going to go to carbon dioxide plus water plus energy, giving off this light and heat. Well, in the bottom equation, if paraffin wax is in the presence of carbon dioxide, no reaction can take place. And so what would we expect to happen? We expect nothing to happen, meaning that the candle is going to go out. Okay? If this is a predictive science, if all this is true. So what I'm going to do, feed this in here, and seal it off with a piece of film. Make sure we get a good seal here. Now I'm going to take my bottle of carbon dioxide gas and I connect it to the hose. And now I'm going to very gently squeeze the bottle. I'll watch the bottom one first. Because carbon dioxide is heavier than air, which means it's filling up that bowl just like it was water. The bottom one goes out first, and then once it gets high enough, the top one goes out. And so we have extinguished those flames by filling this up with an invisible gas, which puts the lower one out first and the upper one. Now, also, it wouldn't be good if we were in a fishbowl full of carbon dioxide gas, because we would be extinguished as well, because we need oxygen in order to live, in order to breathe. And so that's another very interesting observation that you can make, is that we are, in a sense, similar to a combustion reaction going on in our bodies. And so, to kind of further investigate that point, we're going to burn a little bit of food up here. This is a favorite of mine called the Howling Gummy Bear Experiment. Good question, sir? Well, there's not a volunteer for this one. This one involves fire and such. So what we're going to do, I've got a gummy bear here. And so this gummy bear is a criminal, and he's been sentenced to death. Believe it or not, he has. So you see our reaction here. We've got a chemical in this tube called sodium chlorate. And so we're going to add heat with this torch. We're going to melt that into a liquid. And that's going to make it give off oxygen. And that oxygen can then be used to burn this gummy bear. In the equation you see below, we've got sugar in this gummy bear, plus that oxygen is going to make carbon, carbon dioxide, and water vapor. So the first step is to melt the sodium chlorate here. It's getting there. Now we've got molten sodium chlorate Then 2. And then we have a gummy bear. But don't feel too sorry, he is a hardened criminal. Alright, so if we can have the lights. It's kind of a nice burnt cookie smell that will slowly permeate the room. It's quite harmless. It should just remind you of maybe that last tray of burnt sugary cookies that you might have encountered. So, would anybody be interested in seeing that again? Before we do that again, what color did you see when that went off? Kind of an orangish red color, right? Well, that's because this material has sodium in it. See if the correct table sodium is on that right column. A nice burnt cookie smell. We've got sodium that's up there in that top corner on the level 3. Well, this one is the exact same chemical except we've substituted sodium for potassium. And so that's going to cause there to be a change in the way it appears. So be looking for a change in appearance for this version of that reaction. So everything else probably seems somewhat similar, but now we're going to melt potassium chlorate.
While he's doing that, potassium is the element A. Notice that it's right underneath sodium on the periodic table. Right underneath A. Very similar element, but a little bit different.
Alright, we're getting closer. Okay, so molten potassium chlorate, another hardened criminal here, sentenced to death. And let's see what happens this time. If I can have the lights, please. More smoke. There it goes. Yeah, that would be bad. Alright. So that one is the Howling Gummy Bear experiment. Okay, normally that's done in the... Alright, so just to, you got a bit of smoking here, don't you? Now, just to drive home the point, we eat gummy bears as well, remember? And so, what do you think happens when we eat gummy bears? Yes? The acid in our stomach break it down, and then our body metabolically, metabolism, enzymatic process, it takes that sugar and it turns it into carbon dioxide. And so what would you expect to happen if we were to take a volunteer and have them come up here and breathe with us? Like you have you over there in the red. Yeah.
Well,
Why don't we get both of you to come up here? Now we've got human carbon dioxide generators, right? So you can walk on around the table here. And if you could just kind of breathe into that box right there, you'll see what happens with that signal. What's happening over here? On the way to our end, it's going up because he's generating carbon dioxide. Because he ate some food, and the food is turning itself into carbon dioxide. All right, let's see if this guy's making carbon dioxide too. Let me air this out. Sorry about that. We'll air this out. And we'll see if you're making carbon dioxide too. Go ahead and breathe in there. See if the number goes up. Just kind of blow it with your mouth. Just kind of blow it right in there. There we go. He is alive. There it is. All right. So see, we are making carbon dioxide just as much as that combustion reaction did. All right. Thank you, gentlemen. Very good carbon dioxide generators. All right. So let's see what we've got next up here. Next, we're going to go from something that was very hot to something that's very cold. So Dr. Rogers is going to show us some liquid nitrogen.
Okay. This might be the only time in your life that you will ever see liquefied air. This room that you're in right now, like any place you ever go on Earth, is about 78 of 3/4 of the air. It's nitrogen. Nitrogen is right in atomic number 7, upper right hand part of the periodic table, the symbol N. Okay. So nitrogen is normally a gas. The air that we're breathing is a gas. But here it's liquefied. Now, to liquefy nitrogen, we have to get it very, very, very cold. And in fact, this nitrogen right in here is boiling right now at about 196 degrees, 195.8 degrees below zero. Very cold. Now, we're going to see, we want to try to prove that. I'm going to need some help from the people up front. And you need to stay right where you are. And I just want you to read this. Can you... And by the way, 195.8 degrees below zero Celsius is the same as 320 degrees below zero Fahrenheit. What is this reading right now? Can you read it? About 76. So in this room right now, that makes sense, a little bit warm in this room, about 76 degrees. This is a thermocouple. And if I hold it with my hand, is it a little bit warmer?
Yeah.
Ideally, I suppose it should go up to 98.6, shouldn't it? A little bit. What's it up to now?
90.
Okay, so I'm getting close. All right, now we'll put it in liquid nitrogen. Can you still read it okay?
Yeah. Negative 290.
About negative 310. So we're not quite hitting the negative 320. But we're pretty darn close, aren't we? And that's very, very, very cold. If you think, here in Wisconsin, what was the coldest that got last winter? Maybe, what, 30 below, negative 30? So now we're looking at negative 300, more than negative 300. It's very, 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 very cold. And just to show you, this is the liquid. If I pour it, now, if I were to put my finger into there, it would literally freeze my finger. I don't want to do that. Why don't you get the hands down? Let us talk. You'll have a chance to ask questions later, actually. On the other hand, if I hold my hand like this, and pour it on my hand, I hardly feel it because when it hits my warm skin, it evaporates. It turns into a gas. And that little layer of gas insulates my skin from the very, very cold temperature. Otherwise, it heats your skin almost immediately. And because you helped me with temperature reading, when you hold your hand out, come on up here. Pour a little on your hand. And make sure that your hand is pointing downward so that it rolls off. Not too bad, right?
Can I do it?
Maybe later on when we take a break. So that's a very, very cold temperature. Are we now going to look at a very hot temperature?
Yes.
Great. Now, don't say that word again. Oh, it's up there. It's up there. That's all right. I was going to ask you if anybody knew what the name of this burner is. It's named after Robert Bunsen. I'm trying to remember. I think he invented the burner in about Bunsen burner in the 1800s. We are using methane gas, and I don't know if we have that on the slide. There it is, right there. Methane gas is natural gas. It has a formula CA4. I just want to show you a few things about the Bunsen burner.
But it got some sodium.
We've got some sodium on it, and that's why it's giving us a yellow flame. It's a different Bunsen burner that's not contaminated with sodium. The sodium tends to give you that color. You know what? That's all right. By the way, got to show you one other thing. Remember carbon dioxide and fire? We take a match and put it down into liquid or into the nitrogen gas. Match goes out. So nitrogen is like carbon dioxide. Okay, but here we're using oxygen. I think it's the gas.
Maybe air.
It could be, it could be the air. That's right. We've got some sodium particles in the air. You know what? We're not going to worry about it. When we have a Bunsen burner, we can do a couple of things. We have a barrel that has holes in the bottom, and if we turn that barrel so that the holes are closed, cover those holes with the linseed. I'm going to cover them with my hand. We get a fairly quiet flame like this. When we open those holes and the flame gets a little bit noisy, getting closer to where it wants to actually explode, and I think we're getting almost like a kind of an explosion going on there, but a continuous sort of explosive type of reaction. Very rapid, very, very hot. What do you think the temperature of that Bunsen burner is? Somebody want to take a guess? Yes, sir.
Like 400 degrees.
Okay, maybe 400 degrees. Yes.
Maybe 200 to 300?
Would you say that again?
200 to 300?
200 to 300. Okay, we'll take one more guess. Way over there. Yes.
Maybe 140.
Maybe 120. Well, is our temperature still on?
Yeah.
Okay, let's take our thermocouple and we'll put it into that flame like that. You're going to put the thermocouple right into the flame. Can you read it? Are you able to see that right now? Okay, what is it reading right now? Okay, I'm going to get it closer to the flame. Okay, now I'm going to put it in the flame. I'll put it in the bottom of the flame first of all. Okay, now I'm going to raise it to about right there. Notice what the thermocouple wire is doing. What are we getting for a temperature now? Right, over 2,000 degrees Fahrenheit. Over 2,000 degrees. That is hot, isn't it? hot enough to cause our wire to glow. And it's kind of interesting that when we put it lower in the flame, where the gas isn't burning very completely yet, the temperature goes down. When we raise it up in the flame, the temperature goes up. Now if we go higher, go way up to here, the temperature will drop. So that's our Bunsen burner flame. Anybody ever asked you what a Bunsen burner is? Now you know. What do we got next?
Methane bubble.
Oh, we're going to do some methane bubbles. Now this one's my favorite. And Dr. Ray is going to help me out on this. How's everybody doing? Are you okay? You're not falling asleep yet? I got some bubble stuff. Not very much, but enough to blow some bubbles. And we're going to, instead of blowing bubbles, well, let's see. Do I have a wand here? Let me try something. I'm not a very good bubble blower. There we go. Notice where they went. They went down because they're a little bit heavier than air. Now we're going to try methane, natural gas, and we'll blow a bubble. Let's see what this one does. What does it tell you about methane?
It's lighter than air.
Perfect. It's lighter than air. And remember, carbon dioxide is heavier than air. Now, Dr. Ray, and you know what? She's going to... He is going to... We already know that methane burns. I mean, we saw that in the Bunsen burner. Big bubble. One more time.
Two more.
Sure. So the reaction that we're doing, both in the Bunsen burner, in the bubbles, and as well as what we're about to observe in a coffee can filled with methane, is this reaction. So you've got methane, which is CH4, one carbon and 4 hydrogen atoms, combined with 2 oxygen atoms, O2. So there's 4 atoms, 2 molecules of oxygen, and that's going to carbon dioxide again. There's a theme. You notice we make carbon dioxide, the gummy bear make carbon dioxide, methane's making carbon dioxide. This is a combustion reaction. We've got carbon dioxide plus 2 molecules of water. And so you see a burner. Perhaps any of us have a gas-powered stove at home. Looks like that. We've got a few folks here. And so that's the same reaction happening with natural gas stove. But methane does not explode or burn, or it doesn't explode at least, unless there's a very specific concentration of both methane and oxygen. And so Dr. Andres is going to give us a demonstration here about how the combustion or explosion of methane is affected by the amount of oxygen that is present.
This is what we call the explosive limit. We're going to try to reach that explosive limit of methane. And the way we're going to do that, take our natural gas again, but this time instead of being connected to a Bunsen burner, we are going to put the hose into the hole inside of the can. You can see that hole inside the can. Notice there's a hole in the top of the can. And we're going to turn on the methane. Give it a little time.
Oh, yeah.
Methane flame again. But this time what we're going to do, notice that that's kind of a yellow flame. It doesn't have that noisiness that we had from the Bunsen burner. We're going to pull this hose out of there and turn off the gas. So right now, all that's happening is the methane that's in the can is burning. And you guys already know that methane is lighter than air. Somebody said that. It's less dense than air. And so it's rising. It's rising out of that top hole. In this side hole right here, air is coming in. I put my finger over that side hole. Keeps the air from coming in so the methane can't get out, as you see. But as that air is going in, it's mixing with the methane that's in the can. And notice how the flame changes over time. It starts out very yellow, but as the time goes on, it's going to become less yellow and more invisible, more like the Bunsen burner was, although that Bunsen burner wasn't as invisible today as you sometimes have it. But it's getting full. It's actually turning into a little bit hotter flame. But when it gets to the right mixture of methane and air, then whatever methane that's still in the can, will burn very rapidly. That's what an explosion is. An explosion is a very rapid burn, rapid chemical reaction. Now I'll be quiet and we'll just wait. Okay, everybody, we want your attention back. I know this is getting long, but you know, it's still a lot of good. I hope you'll bear with me. We're going to try a new fuel this time. Instead of a gas, methane is a gas. And you know what gas is. Gases are around. You can tell that gases are around. I wave my hand at you can't feel the air. But this is a liquid fuel. This is a fuel that's in gasoline. Ethanol. You go to the gas station, what does it usually say? At what percent of ethanol is in gasoline? Well, no, it's a little less than that, yes. 5%? No? Yes, sir. 10% is right. I always look at that when I fill up my car. See if I can fill my car up too often. But about 10% of the gasoline is ethanol. You put a little bit of ethanol into these bottles. We don't need very much. One thing that's very interesting about fuels, at least the common fuels that we use, is that to really burn, especially to burn rapidly, they need to be in the form of a gas rather than a liquid. And so we're going to put ethanol in each of these bottles. A little bit.
Any volunteers? Maybe someone toward the back that hasn't gone. You back in the back with the multicolored shirt there.
All right. So stay right in front here. We are going to. We have a light bulb. Light bulb is ready. Can you take the light bulb out of there and hold on to it? This is a Tesla coil, everybody. And I just want to give you a feeling for what the Tesla coil does. See if we can find it. Tesla coil produces about 10,000 volts. If we hold it near this, I don't know if you folks over there can see this. We hold it near that do that. You get a spark that jumps about an inch. Usually if you get a spark that can jump an inch, you've got about 10,000 volts. So what we're going to ask our volunteer to do is to hold that light bulb, hold it away from your face. I don't want the spark to jump to your nose. And we're going to put that electricity into that light bulb. You can see it flowing right into her hand. Now the one thing we didn't tell her is that her hair would start standing up when we did this. Sorry about that. You can go to the bathroom and comb it. No, that's not true. So you can see that electrical energy flowing into her hand. I think we'll not worry about the overhead. What we're going to do is we're going to ignite the ethanol.
All right, we got number one here. Are we all ready? This is just like a spark plug here.
Okay.
So we're all ready to go?
You can use the spark to ignite the ethanol.
Fire two. Getting bigger. Here comes a bigger one.
So again, you saw the explosive nature of ethanol. We can make explosions if we have the right fuel. Okay. Now sometimes you can get the gases to burn very gently, like in the Bunsen burner. Here, we're going to add a little bit of a fuel called hexane, which is also in gasoline. It's weaker. And we want you to see that there's not very much in there. A little bit of liquid in the bottom. I want to show you that these beakers are empty. Okay? And if I take a match, a lighted match, and put it in any of these beakers, they don't have carbon dioxide in them, they don't have nitrogen. Well, they do have some carbon dioxide, not very much, mostly just air, which is oxygen, nitrogen, and the match burns inside the beaker. But now what we will do is we will pour not liquid, but only vapor. Or the gas that's being produced as the hexane vaporizes. Pour that gas into this beaker. See that vapor burning. Everybody, this is why when you fill your car up with gasoline, you see there's a sign that says no smoking, no open flame, because the same thing can happen as you put liquid fuel in your car. If vapors come out of the gas tank, and if there happens to be a burning cigarette on the ground, or a smoking cigarette, those vapors will catch on fire with that, and you could have a very major fire. People actually died in accidental fires from this sort of thing. Okay.
All right, next up is down.
Yeah.
So let's look at some experiment with steel wool here. So steel wool you may have encountered maybe helping somebody sand down a wood surface or something. Fairly common material. And so if I burn steel wool in air, it's relatively unexciting. So yeah, it smolders a little bit. It's a little bit sparky, but not really a sustained flame at all. It just kind of eats up each of these little fibers of steel wool here. However, what do you think is going to happen if we put oxygen in the presence of that steel wool? This is pure oxygen. So our atmosphere is 20% oxygen, but this is 100% oxygen. And so what do you think is going to happen here? So if I open this tank and I flow a slow flow of oxygen here, I'm now filling this container up with oxygen gas. And so now, if I take this steel wool piece and I ignite it, and I drop into that pure oxygen environment, it burns very rapidly, very hot, very quickly, and finally makes this molten, cracks the beaker, it gets so hot, makes this molten, makes this molten piece of glowing red hot iron.
I would have never believed that you could actually get steel or iron burned until I saw this experiment.
Yep, it's amazing. And so this is just a really brief little history lesson. This was a lesson learned the hard way by the scientists at NASA. Because the Apollo 1 disaster, these three gentlemen were doing a test of a module, and they had their capsule filled with 100% oxygen. And sadly, a fire began, and it went through so quickly, these men died because the people, the engineers at NASA, obviously didn't pay attention during general chemistry class when we talked about the oxidation of iron. And so even metal can burn easily. Relatively non-reactive metals can burn. And so that was a lesson learned the hard way. And that's just a quick example of how something that's normally not very combustible becomes highly combustible whenever it's in the presence of pure oxygen. So magnesium?
Yeah. One other thing. Again, we don't think of metals as burning, yet they can burn. And you just saw iron or steel burning, and it takes pure oxygen to get it to burn. That was so helpful. This is magnesium metal. And I'm just going to hold this so that everybody can see it. Just a little strip of magnesium metal. You guys will be able to see very well. A little strip of magnesium metal. You have a bicycle. There's a very good chance that the wheels on your bike are made out of magnesium, or maybe not pure magnesium. It's probably mixed with aluminum and other metals. They usually call it magnesium alloy. But magnesium is in lightweight metals. Lots of times airplanes have magnesium. That's probably one reason why when the airplanes hit the World Trade Center, they burned so badly is because they were loaded with magnesium. Magnesium will burn even without additional oxygen. This is the oxygen that's in the air. Now you're going to see a very bright flame. If it's a little bit too bright for you, you might want to just look a little bit off to the side. It's amazing how chemically reactive the metal magnesium is.
I'm staring into it.
Of course. And so all that's left on the end of our tongue is a little piece of magnesium oxide, which is sort of like rust, except it's magnesium oxide instead of iron oxide. And that's what happens when magnesium bursts.
All right. So here's a favorite of my general chemistry class. So you notice that we've got some balloons that have been sitting here all this time. Anybody want to guess what those are filled with? Yes, in the middle. Oxygen? That's an interesting guess. Another guess, sure. Helium, another very good guess. Any other guesses? Yes, sir. Air, it could be air, but notice they're floating. So we expect to be less dense than air. If we fill with air, it would probably just be on the ground. It must be the same material. Any other guesses? Yes, sir. Methane, could be methane. Well, it's actually, you got the answer? Hydrogen, exactly. So if we look up here at the periodic table, hydrogen is this top, so the big H. Helium in the other corner, Hg. So if you go get a balloon filled up at the florist or the grocery store, that's going to be filled with helium. Helium is a very non-reactive, stable, but very light gas that will bring things up. However, hydrogen is also a very light gas, but it's highly reactive. Quite opposite of helium. And so we've got 3 balloons here filled with helium. And so what do you think is going to happen if, say, I don't know, filled with hydrogen? We set it on fire. That's helium? Yeah. I meant hydrogen. These are hydrogen-filled balloons. Notice I am taking earplugs out. So I encourage you folks to do this little number. Take your hands and cup them so that you seal it here in the front, and so back behind, you're cupping it so you're hearing from behind you now. And so what you'll hear is the little pop that will bounce off that back wall and then forward, and this will make it not quite so loud. So make sure you got your hands cupped, point your ear backwards, all right? So I've got a candle on the stick here. And so we'll do this one first, and then we'll take a look at what's going on before we do the other 2. So let me actually dim the projector up here. So everybody turn your ears around backward here. Everybody ready? Another historical disaster. So what happened was the German folks at the time, back in the 30s, did not have an abundant source of helium. And so they filled their Zeppelins, their blimp-like objects, they filled them with hydrogen, which was a very, very bad idea. Because as you can see, it's explosive. If it catches on fire, it's over in a hurry. So on the 6th of May, 1937, one of their dirigibles called the Hindenburg, after that guy peeking at you up in the top corner there, caught on fire over the U.S. and fell to the ground and burst a ball of flames, and a lot of people died. Not everybody, but a lot of them did. And so you see that right now it's not combusting because it's just that pure hydrogen there that's present in that balloon. But if it has just that little spark, just that little flame, it will make it go off. So what we're going to do now is we're going to set off these other 2. All right, everybody ready?
Yeah. No, I'm not ready.
3, 2, 1. Uh-oh. You ready? Quick note, how much energy do you think is given off by that flame? Would you believe that that's the exact same amount of energy in less than 1.5 of those Austin sandwich cookies? When you eat those little sandwich crackers, that explosion would be equal to 1.5, or a little less than 1.5 of those crackers. So it's no wonder we gain so much weight. We got explosions going on inside of us, right? Not really, because those explosions are occurring metabolically. That combustion is occurring metabolically, happens slowly. So instead of being less than a second, it occurs over days of time. It could also be enough to light a 60-watt bulb for almost 45 minutes. So that's a lot of energy. So our end here, we're going to talk about an internal combustion engine, and how you can harness explosions like what we've been observing to do work. So we can live off of combustion, we call it combustion. We can also do work with combustion so that we can go from point A to point B. The bus that runs here has an internal combustion engine, and that's the way that it works. So Dr. Anderson is going to tell us about this clear internal combustion engine.
Okay, everybody, this is, anyway, there's a good chance that some of you girls, and I'm sorry to some of you girls, but there's a program that's held at Stout in the summertime called Steps. Have some of you thought about going to Steps this summer? Okay. If you do, there's a good chance that I'll get to see you again because I'll be teaching it. This engine was actually bought by the Steps program. We'll actually demonstrate this again this summer. This engine, I think this was about $2,000 when we bought it. It might have been more, maybe $2,000 or $3,000. It's a very, very special engine. Sort of reminds me of the engine on my lawnmower because it's about the same size. But the difference is it has a piston inside that is visible because the cylinder is made out of glass. The engine on your lawnmower has a cylinder that's made out of steel, most likely, and that you can't see. You also can't see the crankshaft turning inside like we can when we turn this. You can see the piston moving up and down. But this is an actual engine, and if I get this position right, it runs on fuel. It uses explosions. We've shown you a bunch of explosions. It uses a spark. We showed you the Tesla coil that spark ethanol to get it to burn. Well, the fuel that we are going to use in this engine, we could use ethanol. We could use gasoline. But we're going to use heat, which is actually isopropanol. It's another alcohol like ethanol. I'm going to take a little of this isopropanol, on the right container here. I'm going to put it in the fuel tank. This little white container here is the fuel tank. And what we have in a 4-stroke internal combustion engine is intake, where a mixture of fuel and air. First of all, the fuel is vaporized in the carburetor. The fuel is changed from a liquid to a gas. Just like in these bottles, we vaporized some of the ethanol, and that's what exploded. Well, the isopropanol will be vaporized in the carburetor, and it's taken in to the cylinder, drawn into the cylinder as the piston moves downward. Then, it's compressed as the piston moves up. We get compression. And then when the piston gets to the top, the spark plug sparks, just like that Tesla coil sparks. And we get ignition, and that ignites the fuel. And then finally, the piston gets pushed downward by the explosion, and then the gases, carbon dioxide and water vapor, are exhausted out the exhaust pipe with the muffler. So, if this is going to work, and I hope it'll work, it started for me yesterday, I've only tried it one time, so I don't know. We're going to try to get this thing to operate, And this has a real high-tech starter. Doesn't have an electric starter. Whoops. Yeah, no, that's okay. It works. I'm going to pull it one time with the electricity turned off. I'll open the needle valve to get some fuel to come down into the carburetor. I'm going to put my finger over the air intake and stroke it so that the fuel is actually drawn down into the carburetor. So now, if you ever start the engine on your lawnmower, there's a little choke lever. Well, that choke lever does exactly what I did by holding my finger over the carburetor. So now, hopefully all this build-up, this better work, or else we're going to flip on the electricity. And start. You got your ready to turn the lights down. Just try to slow it way down. Sorry, I just pulled the electric wire off of the generator. We're going to try that again. And I'll tell you what, I'll turn it like this time. As it's operating, you can see the crankshaft turning inside. Let's see if we can start it one more time. If it won't start, we'll worry about it. Let's start. So explosions are very important to us.
That's what we got prepared for you.
So thank you. You guys have been really wonderful. Now, before we take a break, and I think the teachers can tell us